This is Physics 2212, Lab 4, Circuits. In this lab report, I will first introduce the experiment and explain the experimental procedure. I will then follow with the results, discussion, and the conclusion. The purpose of this lab is to investigate the behavior of circuits containing resistors in series and parallel, to measure the conventional current and potential difference in an actual circuit, and to examine RC circuits and find its time constant. The fundamental principles of this lab include the node and loop rule, which are statements of the conservation of charge and energy respectively. The node rule states that current in must equal current out, and the loop rule states that the potential difference of a round trip must equal 0. Ohm's law relates voltage to conventional current and resistance, and capacitance is the capacity of an object to store electrical charge. It is equal to the charge divided by the potential difference across the capacitor. A linearization equation is also provided on the slide to be used to calculate the time constant RC from experimental data. A preview of the results is that the current measure was 0.02 amps and the potential difference of the loop was 0.2 volts, close to the theoretical 0 volts expected. Increased resistance led to longer charge and discharge times of the capacitor, and the RC constant of the 33.3 ohm bulb was 45.45 seconds. For part 1 of the experiment, the system is the multimeter and the surroundings of the circuit and everything else. For the RC section of this lab, the circuit is the system and the surroundings is everything else beyond the circuit. The key assumptions of this lab include ideal wires and circuit components that have no internal resistance and steady-state conditions. The predicted current of the circuit was 0.0204 amps using the loop rule. The experimental current found was 0.02 amps for both ammeters in the circuit, and if the ammeter is set up backwards, the magnitude is the same but the sign is changed. If you were to replace one ammeter with a voltmeter, the experimental current is 0 amps, the experimental delta V is 2.7 volts, and the simulated is 3 volts. They match closely but likely differ due to unideal circuit components and age of the cell that reduces its EMF. The current is 0 because the circuit is not closed. Also on this slide is the potential difference across different parts of the circuit. They should all sum to 0, but experimentally they sum to 0.2 volts. This is due to inevitable experimental deviations from theory and assumptions and error. The graph depicts the change in potential difference across the circuit. The 0.2 volt sum that I found experimentally is included, which is why the line does not approach 0 at the end of the circuit. The voltmeter has a very high internal resistance, so very little current flows through it, leaving the ammeter reading unchanged. It also does not change across the 100 ohm resistor. The reading on both ammeters increases to 0.06 amps when connected in parallel to the 100 ohm resistor. This is because multiple paths are available for the current to flow, which reduces the overall resistance in the circuit. The experimental resistances of the circuit components are also calculated and presented on the slide. For part 2 of this experiment, including a resistor capacitor circuit, this was made using a 1 Faraday capacitor, a 3 volt battery, and an 8.3 and 33.3 ohm bulb. The light bulb glows initially and then dims once the capacitor is fully charged, and as the capacitor discharges, the bulb glows again until it dims completely. The charge and discharge times for both bulbs are presented on the slide, and a greater resistance limits the current flow, so the capacitor takes longer to charge and discharge. For part 2 continued, determining the RC constant experimentally. This is done with a graph that plots ln of delta V divided by delta V initial versus time. According to the linearized lab-specific formula presented in the introduction, the slope is equal to -1 over RC, RC being the constant that we are trying to calculate. So the RC was 45.45 seconds. Lastly, for the results, discussion, and conclusion, possible sources of error include low precision of the ammeter, as many decimal places are not available, and no consideration of unideal circuit components and factors like effectiveness of the battery. As for the additional questions, an ideal ammeter has no resistance, so it would read a slightly larger current. The simulated wires would also have 0 resistance, so the round-trip potential difference would likely be exactly 0. The ideal model charges the capacitor instantaneously, but that is not true for a real-life circuit because all the components have a non-zero internal resistance. A quantitative experiment was not conducted with an ammeter, but I would expect that although it is quick, the charging is not instantaneously. To conclude, the current measure was 0.02 amps, the potential difference of the loop was 0.2 volts, increased resistance led to longer charge and discharge times, and the RC constant of the 33.3 ohm bulb was 45.45 seconds. Thank you.